solve the equation, where x, y and z are non-negative integers. This is a Diophantine equation. There are 3 variables in one equation. How to solve this equation? Usually there are different ways to solve this kind of equations. For example, one way might be to convert the equation to the product of 2 algebraic expressions of variables of interest equals a number. Due to the variables of interest are integers, so each algebraic expression is an integer factor of the number. This leads to a system of equations. Then solve the system of equations, and find the integer solutions of the original equation. By rearranging the equation, we have 3 to the power of y equals z squared, minus 4 to the power of x. 4 is 2 squared. So we can now write 3 to the power of y equals z squared, minus 2 squared all to the power of x. We know that a to the power of m, all to the power of n, equals a to the power of mn, which is equal to a to the power of nm, which is equal to a to the power of n, all to the power of m. By applying this, 2 squared all to the power of x is equal to 2 to the power of x all squared. So we can now write 3 to the power of y equals z squared, minus 2 to the power of x all squared. Now the right side of the equation is the difference of 2 squares, which is equal to z minus 2 to the power of x times z plus 2 to the power of x. As x, y, z are non-negative integers, so z minus 2 to the power of x and z plus 2 to the power of x must be factors of 3 to the power of y. So we let z minus 2 to the power of x equal 3 to the power of k, and z plus 2 to the power of x equal 3 to the power of y minus k. Where k is a non-negative integer, and k is less than y minus k, as z minus 2 to the power of x is less than z plus 2 to the power of x. Equation 2 minus equation 1, we have 2 times 2 to the power of x equals 3 to the power of y minus k, minus 3 to the power of k. As 3 to the power of y minus k, and 3 to the power of k, have a common factor 3 to the power of k. So they can be factorized and written as 3 to the power of k, times 3 to the power of y minus 2k, minus 1. If k is greater than 0, then 3 divides 3 to the power of k, times 3 to the power of y minus 2k, minus 1. From equation 3, we know that 3 divides 2 times 2 to the power of x. This is a contradiction, as 3 does not divide 2 times 2 to the power of x. Therefore, k must be equal to 0. From equation 1, we have z minus 2 to the power of x equals 1. From equation 3, we have 2 to the power of x plus 1 equals 3 to the power of y minus 1. As x is a non-negative integer, so we divide the problem into 2 cases, either x equals 0, or x is greater than or equal to 1. Case 1, x equals 0. From equation 4, we have z equals 1 plus 2 to the power of 0, which is 2. So z equals 2. From equation 5, we have 3 to the power of y equals 1 plus 2 to the power of 1, which is 3. So y equals 1. Therefore, x equals 0, y equals 1, and z equals 2. It's easy to verify that this is a solution of the original equation. Case 2, x is greater than or equal to 1. Then 2 to the power of x plus 1 is congruent to 0 modulo 4. From equation 5, we know that 3 to the power of y is congruent to 1 modulo 4. So y must be even. We let y equal to m, where m is a non-negative integer. Substitute y equals 2m in equation 5. We have 2 to the power of x plus 1 equals 3 to the power of 2m minus 1, which is equal to 3 to the power of m all squared. The right side of the equation is the difference of 2 squares, which can be written as 3 to the power of m minus 1 times 3 to the power of m plus 1. As x and m are non-negative integers, so 3 to the power of m minus 1 and 3 to the power of m plus 1 must be factors of 2 to the power of x plus 1. So we let 3 to the power of m, minus 1, equal 2 to the power of n, and 3 to the power of m, plus 1, equal 2 to the power of x minus n plus 1. Where n is a positive integer, and n is less than x minus n plus 1, as 3 to the power of m, minus 1, is less than 3 to the power of m, plus 1. Note that n cannot be equal 0, as when n equals 0, from equation 7, we have 3 to the power of m equals 2, which has no integer solutions. Equation 7 plus equation 8, we have 2 times 3 to the power of m equals 2 to the power of n, plus 2 to the power of x minus n plus 1. Divide the equation by 2, we have 3 to the power of m equals 2 to the power of n minus 1, plus 2 to the power of x minus n. 2 to the power of n minus 1, and 2 to the power of x minus n, have a common factor 2 to the power of n minus 1. So they can be factorized and written as 2 to the power of n minus 1, times 1 plus 2 to the power of x minus 2n plus 1. If n is greater than 1, then 2 divides 2 to the power of n minus 1, times 1 plus 2 to the power of x minus 2n plus 1. From equation 9, we know that 2 divides 3 to the power of m. This is a contradiction, as 2 does not divide 3 to the power of m. Therefore, n must be equal to 1. From equation 7, we have 3 to the power of m equals 2 to the power of 1, plus 1, which is 3. So m equals 1. We know that y equals 2m, so y equals 2. From equation 5, we have 2 to the power of x plus 1 equals 3 squared minus 1, which is 8. So x plus 1 equals 3, which means x equals 2. From equation 4, we have z equals 2 squared plus 1, which is 5. So z equals 5. Therefore, x equals 2, y equals 2, and z equals 5. It's easy to verify that this is also a solution of the original equation. So there are two sets of solutions.